Good morning, all of you. Today, I Naveen Garg from BSc Chemistry Honors final year. Today, I am going to read a chapter for visually impaired students from the book Pradeep's Physical Chemistry, Volume 3, by Dr. K.S. Kheterpal. Of chapter Molecular Spectroscopy, and topic is Raman spectra. General Introduction, Section 3.35. It is a special type of spectroscopy which deals not with the absorption of electron but deals with the scattering of electron by the molecules. It is observed that when a substance which may be gaseous, liquid or even a solid is irradiated with the monochromatic light of a definite frequency mu, a small fraction of a light is scattered. A relay found that the scattered light is observed at a right angle to the direction of incident. The scattered light is found to have a same frequency as that of an incident light. This type of scattering is relay scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, or a solid is irradiated with a monochromatic light of a definite frequency mu, the light scattered at a right angle to the incident contains a lines not only for the incident frequency but also of a lower frequency and sometimes of a higher frequency as well. The lines with the lower frequency called Stokes lines, and whereas the lines of a higher frequency are called anti-Stokes lines of Raman. Further, observe that the difference between the two frequencies of incident light and the particular scattered light was constant depending only on the nature of a substance being irradiated and was completely independent of a frequency of an incident light. If mu I is the frequency of an incident light and Vs that of a particular scattering light, the difference between the difference delta nu is nu I minus nu s is a Raman frequency or a Raman shift. Thus the Raman frequencies or a Raman shift observed for a particular substance are a characteristics of that substance. The various observations made by a Raman continues that what is called a Raman effect, and the spectra observed is called Raman spectrum. This is the way the simple Raman spectra may be represented as shown. Section 3.36. Explanation for observing relay scattering line and Raman line. When the incident photon hits the molecule, the collision may be elastic or inelastic. The elastic collision means that that of a colliding particle will return with the same energy. Thus, the scattered photon has the same frequency as that of an incident photon. This explains relay scattering or a relay line. However, if the collision is inelastic, still the law of conservation of energy will hold good. Total energy before collision and after collision must remain the same. Thus, some energies may be transferred from an incident photon of a molecule so that the scattered photon has lower energy and hence a lower frequency that of an incident photon. This explains the occurrence of a Stokes lines. Alternatively, some energies may be transferred from an incident photon of a molecule so that the scattered photon has a higher energy than that of a hence higher frequency than that of an incident light. This explains the occurrence of anti-Stokes lines. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher level. Now, if it returns to the original level, it will emit the same energy as absorbed as, and thus we have a relay scattering. However, in most of these cases, excited molecule does not return to the original level. It may return to the level higher than the original level or thereby emits a lesser energy than absorbed. This means there occurs as Stokes lines. Thus, part of the energy of an incident remains absorbed by a molecule so that the molecule has a higher energy than before. Alternatively, the excited molecule may return to the level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines. In this case, the molecule has a lesser energy than before. The different case may be represent diametrically as shown in figure 3.30. Level have been shown equally spaced just for a checking of a convenience. Section number 3.37, polarizability of a molecule and Raman spectra. The Raman effect arise accounts on the polarizability distortion of an electron cloud of a scattering molecule that is caused by electric vector of electromagnetic radiation. The induced dipole moment mu depends on the strength of electric field E and the nature of a molecule. We write mu is equals to alpha into E, equation number 1, where the quantity alpha depends on the nature of a molecule and it is called a polarizability of a molecule. Thus, the polarizability is the ratio of induced dipole moment to the strength of electric field. In case of atoms or a spherically symmetrical molecule, spherical rotator such as SCH4, SF6, etc., the same polarizability is induced whatever may be the direction of applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules, homonuclear or a heteronuclear or a non-spinal molecules, non-spherical rotator, the polarizability depends upon the direction of electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to bond and when it is applied perpendicular to bond, and we write alpha parallel greater than the alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Types of molecules showing rotational Raman spectra. A molecule scatters light because it's polarizable. Hence, the gross selection rule for the molecules to be a rotational Raman spectra is that the polarizability of a molecule must be anisotropic. That is, the polarizability of a molecule must depend on the orientation of a molecule with respect to the direction of electric field. Hence, all diatomic molecules, linear molecules, and non-spherical molecules given Raman spectra, that is, there are rotationally Raman active. On the other hand, spherically symmetrical molecules such as CH4, SF6, etc., do not give a rotational Raman spectra. There are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one reason for the importance of a rotational Raman spectroscopy over an infrared spectroscopy, because of a later requires that the molecule must have a permanent dipole moment, whereas the forms only requires that the polarizability of a molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of a molecule that is a rotating or vibrating is not constant but varies with the frequency of vibration and the rotation. It is a sum up of two pairs. For example, xenon atom has a greater polarizability than helium atom because xenon atom the electrons are more distant from a nucleus and hence the less tightly held by the nucleus, therefore more easily be displaced by the electric field external. The first is equilibrium polarizability alpha naught, that is polarizability when an atom or a molecule are there in an equilibrium position. Second, sum of the polarizabilities of a molecule due to the vibrational, rotational and vibrational motions, each terms depending on the frequency of a rotation or a vibration. Thus, alpha is equals to alpha naught plus summation of delta an upon delta r into rn cos 2 pi nu nt, whereas alpha n is a polarizability associated with the nth rotation or a vibrational mode. Rn is the maximum displacement of an atom involved. Further, the electric field vector of electromagnetic radiation varies with the time in sinusoidal manner, as in E is equals to E naught cos 2 pi nu naught t, equation 3. Substituting the value of alpha and E from equation number 2 and 3 in equation number 1, we get mu is equals to E naught into alpha naught cos 2 pi naught 2 pi nu naught into T plus summation of delta an by delta ar into Rn cos 2 pi nu n T into cos 2 pi nu naught T. This expression consists of three terms. The first term has a frequency of incident radiation and represents relay scattering. The second term consists of a nu naught minus nu n, represents Stokes lines, and the third represents nu naught plus nu n, represents anti-Stokes lines. Section 3.38, the quantum theory of a pure rotational Raman spectroscopy of a diatomic molecule. The selection rule for a rotational Raman spectroscopy of a diatomic molecules are delta J is equals to 0 to plus minus 2, 0 and plus minus 2. The selection rule for delta J is equals to 0 corresponds to the relay scattering, whereas selection rule for the delta G is equals to plus minus 2 gives rise to the Raman's lines as explained below. We know that the energy of a rotational level in terms of a wave number with a quantum number j is given by nu bar is equals to bj into j plus 1, equation number 1. When a transition plays from a lower rotational energy level to the quantum number j to the higher rotational energy level quantum number j dash, the energy absorbed in terms of wave number will be delta nu dash is equals to bj dash into j dash plus 1 minus bj into j plus 1, equation number 2. For the selection rule, delta g is equals to plus 2, that is j dash minus j is equals to 2 or j dash is equals to j plus 2. We get delta nu dash is equals to b into j plus 2 into j plus 3 minus bj into j plus 1, that is equals to b into 4j plus 6, whereas j is equals to 0, 1, 2, 3 up to h so on. Again, for the selection rule, delta g is equals to minus 2, that is j dash minus j is equals to minus 2 or j is equals to j dash plus 2. We get delta nu dash is equals to bj dash into j dash plus 1 minus b into j dash plus 2 into j dash plus 3, that is equals to minus of b into 4 of j dash plus 6, where j dash is equals to 0, 1, 2 and 3 up to so on. Combining the equation 3 and 4, the wave number of a line obtained in a Raman spectra will be given by nu bar is equals to nu bar I plus delta of nu bar. So nu bar is equals to nu bar I plus minus b of 4j plus 6, equation number 5, where j is equals to 0, 1, 2, 3 up to as so on, where delta nu I represents the wave number of relay scattering, plus sign gives the higher wave number called anti-Stokes, and the minus sign represents the lower wave number, that is Stokes line, where from equation number 5 it may be seen that for j is equals to nu dash is equals to nu dash plus minus 6b is first Stokes line and anti-Stokes line, where be the separation 6b from relay scattering. Further, j is equals to 1, 2, 3. The separation between the two adjacent Stokes lines and anti-Stokes lines will be given by 4b. Thus, the pure rotational Raman spectra expected for a diatomic molecule may be represented in figure number 3.32. Next section is 3.39, intensities of lines of a pure rotational Raman spectra. As explained earlier, the intensity of a lines depending on the population of an initial level from where the molecules is excited or de-excited or to the final level. Since the population of a rotational level is shown in a figure 3.20, therefore the intensities of Stokes and anti-Stokes lines varies in a similar manner. Section 3.40, application of a pure rotational Raman spectra. From a pure rotational Raman spectra, nothing the separation between the lines, the value of B can be obtained by the moment of inertia, and the bond length of a diatomic molecule that can be calculated as above explained earlier. Section 3.41. Quantum theory of rotational vibrational Raman spectra of a diatomic molecule. For our larger molecules, the lines obtained due to our rotational transitions are so weak that they are beyond resolution. Hence, we put a pure vibrational Raman spectra. For the selection rules are same for the pure vibrational spectra discussed earlier. That is, delta nu is equals to plus minus 1, plus minus 2, plus minus 3 up to so on. This is, however, in case of diatomic cases molecules, the resolution of a rotational fine structure is sufficient and can be studied. Thus, diatomic case molecules given rotational vibrational Raman spectroscopy as an which can be explained as follows. The selection rule for the transitions are delta mu is equals to plus minus 1 and delta j is equals to 0 and plus minus 2. However, at room temperature, the most of the molecules are in a low vibrational level, that is mu is equals to 0, and therefore the significant vibrational transition from mu is equals to 0 to mu is equals to 1, called fundamental vibrational transition. Restrictions ourselves to these vibrational transitions only. The results obtained as follows. For delta j is equals to 0, delta mu bar is equals to omega e into 1 minus 2 omega e, called cow branch. For delta j is equals to plus 2, delta mu bar is equals to omega e into 1 minus 2 omega e plus b into 4j plus 6, called S branch. For delta j is equals to minus 2, delta mu bar is equals to omega e into 1 minus 2 omega e minus b into 4 of j dash plus 6, called cow branch, representing the value for cow S and O branch by delta mu cow, delta mu bar S, delta mu bar O respectively, and the wave numbers are acting by the radiation of mu I. The wave number of a Stokes line will be follows as mu bar cow is equals to mu bar I minus delta of mu bar cow. Mu bar S is equals to mu bar I minus delta of mu bar S. Mu bar O is equals to mu bar of I is minus delta of mu bar of O. We have considered the case of delta mu bar is equals to plus 1 for the Stokes line, and the anti-Stokes lines are those of a delta mu bar is equals to minus 1. There are usually weak because very few molecules are in an excited vibrational state initially. The rotational transitions accompanied by a rotational transition from mu is equals to 0 to mu is equals to 1, and the rotational vibrational Raman spectrum obtained may be represented as follows. Section 3.32. Advantage 3.42. Section 3.42. Advantages of Raman spectroscopy over infrared spectroscopy. The Raman spectroscopy has a number of advantages over infrared spectroscopy as brief explained below. First is, since Raman frequencies are independent of a frequency of incident radiation, hence by a suitable adjusting frequency of incident radiation, the Raman spectra can be obtained in a visible spectra range, whereas can be observed rather than the more difficult infrared range. Second point is, the Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have a no permanent dipole moment. Such as a study has not been possible by infrared spectroscopy. Section 3. The Raman spectra can be obtained not only for a gaseous but even for a liquid and a solid, whereas infrared spectra for a liquid and a solids are quite diffuse. Because of a ease with the Raman spectra can be studied the molecular structure of a larger number of compounds having a determined by Raman spectroscopy. However, infrared method still continues to remains popular. Section 3.43 Experimental arrangement of a Raman spectra. The experimental arrangement of a Raman spectra is shown in this figure. The fraction of a light scattered is so low due to the normal very weak Raman line were observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamp were be used, gives an intense monochromatic radiation of a wavelength 4358 angstrom, that is 435.8 nanometer. However, with the development of a lasers, which are very powerful source of monochromatic radiation, Raman spectroscopy has been greatly revolutionized.